I'm Lorenzo, flying UAVs without affecting terrestrial UAVs, shared effort with people from AT&T, Professor Melody. Connected UAVs. It investigates the challenges of aerial-to-ground communication from a network provider perspective. Now, as my colleague said, the ability of drones to communicate on high data rate links is instrumental in a series of applications. Live broadcasting and surveillance, cargo and goods delivery, infrastructure monitoring. This and other scenarios require long-range, high-speed network connection. However, connected UAVs differ from traditional ground users for their unique line-of-sight conditions, which is good in a sense, causes great interference to the rest of the infrastructure. So to the base stations, the UAV is not connected to, in a sense. And this is other users' experience service. Now, to motivate our work, we tested the performance of a ground UE and a connected UAV over a dedicated experimental LTE testbed at AT&T Labs. The testbed is made of 2 eNodeBs, 4 cell totals, and what we have done is we put one user on one eNodeBs, connected to one eNodeBs, and the other the UAVs, the one UAV connected to the second eNodeB, and we measure the performance with and without. The performance in this sense are uplink throughput, okay? So the users are generating uplink traffic. And we can see the ground users' degradation when a UAV is present. For this problem has not been proposed yet, and the way to UAVs, which is a conservative choice in the sense that preserves the already working ground-based paradigm, but it doesn't, it basically prevents from high data rate links and all the applications are presented. The way we approach this project is twofold. First, we envision directional transmitters at the connected UAVs and the interference reduction of implementing intelligent direction control. Second, we consider channel-aware trajectory planning when we face the problem moving the drone from A to B rather than moving in a straight line or the shortest path. We consider, let's say, a more channel-aware solution. Now, during the last decade, there has been a significant amount of research on UAV applications for cellular network, few of which focus on extending ground infrastructure to aerial UAVs. Existing approaches mainly work on, let's say, interference mitigation at the ground infrastructure, which often requires base station cooperation and can be cumbersome in a sense. On the other hand, the user directional transmitter has been proposed in a couple of works, but hasn't really been put into practice yet. In this work, what we propose is a controlled service running at the ground infrastructure that continuously monitors the UAV location, its intended destination as a goal, and what its associated base station is. And together with that, KPIs in terms of signal and receive interference at the neighboring base stations. Now, this is possible thanks to the holistic view that a RAN controller has of the infrastructure and the low latency control channel that it has with all these LTE users. So what the control service does is it instructs the UAV with transmission directionality instructions and trajectory path, as so to maximize the uplink throughput of the UAV, still limiting the interference caused to the rest of the network. So in this sense, it tells the UAV where to go and where to transmit. So it needs some sort of cooperation from the UAV that we don't have nowadays in normal ground users. So the problem we're trying to solve is the following. Now imagine one of the applications I mentioned before. Here is just saying a network broadcaster that is intended to have a live stream coverage of a certain event. And during this live streaming, its goal is moving from one point to another point, and it wants to maintain high data rate in uplink, right? What we're trying to solve is how to maximize the uplink throughput of this user, still guaranteeing good performance to the rest of the network, so limited the interference to the rest of the network. And this is the mathematical formulation of what I just said. And this is a mixed integer problem that we solve in a two-step algorithm that I'm going to describe to you. So the first way we approach this problem is we envision a channel-aware characterization of the 3D aerial space. This means that at each location of the 3D aerial space, we discretize the continuous space into a set of finite location. With each location, we associate a set of KPIs. These KPIs can be what the uplink throughput of that specific point would be if the drone was there, and what is the caused interference to the rest of the network if the drone was at that point. And we do this for the whole 3D aerial space of our deployment. And for doing this, we consider line of sight as the dominant path, as is reasonable for flying objects. And we leverage most accurate aerial channel propagation models published. When we apply this characterization to the whole space, and we apply the network constraints that I showed in the previous slide, it looks something like this. So we come up with this 3D aerial space channel characterization. Then we construct a channel-aware graph representation of the aerial space. So we basically take that characterization of the aerial space and we turn it into a graph where nodes represent locations in space, and neighboring nodes are linked to each other toward directed arcs. And the weight on those arcs is basically a function of how beneficial it is for the whole network, for the drone from moving from one point to another to transmit. Finally, we solved the network control problem formulated earlier by solving preferred path optimization problems on this directed graph representation of the aerial space. Our evaluation setup is the following. It compares the performance of two schemes, our approach, so optimal control of trajectory of the drone and its transmission directionality, against a naive solution that only consider, let's say, channel unaware solution. So it goes straight path from A to B, uses traditional omnidirectional transmitters. We base our analysis upon empirical aerial channel propagation models, and we leverage the nationwide LTE base station deployment database of a major US carrier. Here are more implementation details of our evaluation, which are pretty much in line with the LTE standard. And here is how a single experiment run looks like. Our solution on the bottom, on the top is the baseline. Here you can see the baseline basically takes the shortest path from A to B, while our solution optimizes the path in a channel-aware way. And you can see two KPIs shown here. To the left is signal at the UAV, so uplink signal SNR, or receive power in this case, and to the right is caused interference. If you see a little gap there in the plot, it's just because X, Y, and Z are on different scales, but the gaps between the dots is the same. So in this specific case, we can see almost 16 dB signal gain and 9.5 dB interference reduction for the single run. This is for a rural scenario where the red dots are the A0Bs deployed in a small town, let's say, and is for LTE Band 29. More extensive experiments lead to this average result. Those are for 3 LTE bands deployed by AT&T, 3 deployment scenario, rural, suburban, urban, that vary for density of base station and coverage area. And each bar accounts for circa 20,000 paths. Average results are broken down for deployment area, and overall, our performance accounts for a 9.22 dB gain for the UAV, and at the same time for the 5.87 dB interference reduction at the network. Now, the need for a consolidated solution is especially needed when we consider UAV paradigm at scale. Here you can see the throughput degradation of a ground UE user with the number of UAV present in a network. We assume a hypothetical 20 megabits per second uplink throughput for a UE when no UAVs are present, and we compare the baseline solution with our proposed approach with the number of UAVs present. And you can see how the baseline solution makes the UE throughput drop to 3.2 megabits per second when only 5 UAVs are present, and all the way down to 1.9 megabits per second when 10 UAVs are present. Our approach only makes the UE throughput drop to 12 megabits per second for 5 UAVs and 9.27 megabits per second for 10 UAVs. Together with this, we also have improvement on UAV side, but we're mainly focusing on throughput degradation at ground UAVs in this slide. So future work is to develop a low-cost prototype of connected UAV with directional transmitter. We're already working on it. Implementing a full control loop system at the infrastructure, and we are envisioning on doing this with open software, LTE stacks, such as Open Air Interface or SRS LTE, so moving toward softwareization of the network. And sorry for the typos, but it's in the future work is also, we want to extend the support for multiple UAV joint trajectory and directionality optimization. This concludes my presentation. With this, I'm glad to take any questions.